So you're having it join on its own Wi-Fi as a separate device. Is that what your approach has been? Yeah. Yes, I see. Yes.
Yep, it's up for me.
It's up now. I can no longer hear you. Is your mic on now?
Can you hear me now?
Yes.
All right. All right. And let me start the recording. Well, the recording's going, I guess. All right. Can you still hear me?
Yep.
Yes.
All right, good. So I felt the lecture last time on Monday maybe obscured the forest for the trees. So I wanted to start today by recapping in 3 pictures the main steps of the argument last time. Remember, the argument took as given the 2 basic cancellation lemmas and showed how to use those lemmas to cancel all the handles for a Morse function in h-covvordism, and thus prove the h-covvordism was a product, dimensions greater than or equal to 6. So there were 3 steps in this argument. So I'm recapping that. There were 3 different steps covering 3 different cases with 3 different arguments. Critical points of index 0 and n. So that was the first step. The second step was index 1 and n minus 1. And the third step was any 2 less than or equal to k less than or equal to n minus 3. It was done homogeneously by induction, starting at the lowest critical point. For step 0, there was really nothing to do but observe that if you look at the beginning part of the h-covvordism under the Morse function, here you'll have boundary minus of w cross some interval -1 to a half. And then you'll have these critical points of index 0. And for one of them at least, there will be a critical point of index 1 that goes from boundary minus w to the ascending manifold for this critical point. There's nothing to do now except invoke the first cancellation lemma. You cancel p and q. For n, you simply turn the Morse function over. Critical points of index n become critical points of index 0, and you do this for minus f. That's the first picture. That was very, very simple, nothing to do. And the second picture, canceling critical points of index 1, you could do this by the general argument. Well, so we have some critical points of index 1, p1 to pr, let's say. And then, so these are index 1 critical points, and we have index 2 critical points, q1, qs. So here are the critical points of index 1. They're ascending manifolds. Critical points of index 2, I'll put them over here. These are the q's. Okay. we could do the general argument if there were a proper subset of the Q's whose descending circles normally generated the free group generated by the one handles, by the critical points of index 1. So if you look at the fundamental group of the part of the manifold from -1 to 1.5, this is a free group generated by the critical points P1 to PR, or rather, you take their descending arcs and boundary minus of W is connected, you close those arcs up to make loops, and those loops give you, connect them to the base point, they give you free generators for the fundamental group. The critical points of index 2 produce circles in this level, and those circles, of course, become trivial when you add the cap. So the fact that you're creating a simply connected manifold at level 2 means that the circles of the descending manifolds of Q1 to Qn, in fact, normally generate this group. So the descending spheres for the Qi, the elements they represent normally generate this free group, F. Okay. You could do the argument of a cancellation argument if you knew some proper subset also normally generated. So suppose maybe the spheres for everything except the first one normally generate. Okay, so suppose you had that. Then you could simply take the first critical point, move it up above level 2, and its boundary would be a circle in level 2. Level 2 is now simply connected because level 2 is the quotient of the free group F by the normal subgroup generated by the other critical points, which you pass before you get to level 2. So that's a simply connected manifold, and you could do the isotopy argument that I'm going to draw a picture of in just a second for this critical point. So you wouldn't have to add a new critical point as we did using a birth if you knew a proper subset of the Qi normally generated the free group. But there's no reason to assume that. No reason that should be true. And what we did was we created a situation in which that was true by adding a birth death, by adding a birth that put in one more critical point of index 2 and a critical point of index 3. Well, the critical points that you already had of index 2 did normally generate the fundamental group. So I have this extra one now. So our picture is, here's level 2.5. Here are the critical points of index 2. Here's level 1.5. And the critical points of index 1. There's Q1, QS, P1, PR. Unless they were trying to cancel P1. So what we did was we went up above level 2.5 and we put in a new critical point of index 2 and a critical point of index 3, Q prime 3, a canceling pair by a birth. So these are critical point of index 2 and 3 that cancel each other, and they sit in some small ball up here. So we perturb the Morse function in a ball to create these two. Now, at level 2.5, we have a circle that meets the ascending manifold for P1 in a single point. Transverse to the ascending manifold of P1 meets it in a single point. I had to construct that circle. I now take the descending disk for this new critical point that I've created, and I guess push it down to level 2.5. So I have two circles in a simply connected manifold of dimension at least 5. So those circles are isotopic. I display the isotopy like this. I deform the vector field by the isotopy lemma. And now the descending manifold from this new critical point crosses the ascending manifold. Sorry, did it to the wrong place. It comes over here. So the ascending manifold. So here's the circle dual to the ascending manifold of P1 meets it in one point. Here's the boundary of this new critical point we put in. These are circles in a simply connected manifold of dimension at least 5. So I do an isotopy over, and then when I descend this manifold, this descending manifold further down, it meets the ascending manifold for P transversely in a single point, and then you cancel P1 and Q sub 2 prime, because you have a canceling pair with a single intersection. So that was the picture for critical points of index 1. You flip it over for critical points of index n-1. And just to repeat, I would not have needed the birth theorem if I knew there were an extra critical point that I could raise above level 2, above level 2.5, and keep level 2.5 simply connected. In other words, if there were a proper subset of the critical points of index 2 whose descending manifolds normally generated the free group we have at level n plus 1.5, but no reason to assume that. So we arrange it. And the last one is a handle slide. So now K, the smallest index somewhere between 2 and n-3, we're going to do a handle slide. Okay. So I have my critical points of index K down here. Here's the level set K plus 1/2. Critical points of index K plus 1 up here. So P1, PR, Q1, QS. And I have the boundary map from the free abelian group generated by the Q's to the free abelian group generated by the P's. That's the boundary map in the chain complex, which, because there are no critical points of index K minus 1, the chain complex looks like this. And the boundary map, because there's no homology, this being an h-covvordism, this is surjective. So then by this algebraic manipulations, you can change the basis so that the first basis element algebraically cancels P1, meaning the boundary of the first basis element under this boundary map is the element generated, has intersection 1 with the ascending manifold of P in the intermediate level. But we have to be able to mimic the algebraic manipulation of the bases to get a good basis by changes of the Morse function and the gradient-like vector field in order to mimic those changes of bases, so the changes of bases become represented, so that the new bases become represented by the descending manifolds of the critical points. And 2 of the 3 are clear. Permuting the basis, you just change the order of the handles. Multiplying a basis element by -1, you just change the orientation of the descending manifold. The last one was E1 goes to E1 plus E2, and the others are unchanged. And that's the one where we have to do a handle slide to realize. So the picture I drew there was to take, so we're going to try to make the descending manifold out of the first critical point, which is labeled Q1. I want its boundary to be the sum of the boundary of the current Q1 and the current Q2. Okay. So what we do is we raise Q1 up to a higher level. And then we have Q2 and all the others down here. Okay. And we look at the ascending manifold from Q2 and the descending manifold from Q1 at some intermediate level. So Q1 is a critical point of index k plus 1, so its descending sphere is a k sphere. Q2 is a critical point of index k, so its ascending manifold is of dimension Sn minus, sorry, this is critical point of index k plus 1. This is also a critical point of index k plus 1. So its ascending manifold is a sphere of dimension n minus k minus 2. These sit inside F inverse of L, which is of dimension n minus 1. So the picture will be here 2 circles in 3 space. So if n were 4, which of course is not the case, but let me draw the picture, I would have 2 circles. So the sum of their dimensions is 1 less than the dimension of the total ambient manifold. And the I'm going to perform an isotopy on this descending manifold. The track of the isotopy is going to cross the other circle in exactly 1 point. It's clear what to do. You connect these, choose a point here and a point here, and connect them by an arc, which otherwise misses these 2 circles. And the track of the isotopy just runs along this arc until at the end it goes like that. And the track of the isotopy is this finger or tongue that's sticking out, and there'll be 1 point, transverse point of intersection. When you perform the isotopy, that will change and use a gradient vector field, push the gradient vector field by this isotopy. That will change the descending manifold of Q1 until its boundary is the sum of the 2. I'm going to draw you a different picture for this, which is more the surgery picture. You have 2 handles. Again, handle for Q1 and the handle for Q2. And you're going to do what's called a handle slide. So again, you need a path joining this boundary to this one. And again, you're going to do a tongue or finger move. You're going to push this circle or the sphere out until it comes right up and is flush with this sphere. And then you're going to do a lasso. You're just going to throw this thing like a rope over the critical point. So in the end, you're just going to throw this over the critical point, and in the end, you get an isotopy. Again, a finger move that goes all the way out here. And you see, as you throw this loop over the top, you're passing the ascending manifold in a single point. And your new disk will look something like this. Okay. So that's the handle slide. And in this picture, it's clear that the new boundary is the sum of the homology class of this circle, this sphere, plus the homology class of this sphere. So that's what allows you to realize this simple transformation, which is a third of the elementary transformations. So once you do that, you arrange that Q1 has a descending manifold that algebraically cancels the ascending manifold for P1. Namely, it meets algebraically in 1 point, though it may meet geometrically in several points. Use the second cancellation lemma to cancel P1 and Q1. And you go by induction on K. So that's the recap from last time. I don't know if that made it clear or not. I hope it did. Anyway, these are the essential ingredients in each of the three cases. Handle slide in this case, this creating a new critical point, which is not needed to kill the fundamental group, and doing an isotopy in the second case, and really nothing to say in the zeroth case. All right, so that's the recap. What I want to talk about now is how you reduce the second cancellation theorem to the first. And this is really what I'm going to be explaining is usually called the Whitney trick. And I'm going to set it up first, not in the context of an h-covvordism, just in the context of submanifolds and an ambient manifold. So to keep from having to write -1s all over the place, let me let the ambient manifold be MK, and inside there I have submanifolds XR and YS and M. They're all compact, connected, and orientable to all three of them. And okay, I'm going to, so R plus S here is K. So these are manifolds of complementary dimension. I'm going to suppose they're in general position. So here's X, R, and here is Y, S, and I have, of all the points of transverse intersection, I have two that I'm concentrating on. There may be others, but let me not call them X and Y. Let me call them, let's say A naught, or A and B. There are 2 points of intersection. Okay, there may be others, but they're not going to be relevant for this argument. So the first thing I have to do is, the first assumption I have to make is that there's canceling signs between these 2 points of intersection, as is indicated in this little picture. So I choose arbitrarily orientations for X, Y, and M. Okay. And then once I do that, there's a sign epsilon of A equals plus minus 1, and epsilon of B equals plus minus 1. That is the sign of intersection of X dot Y at A and X dot Y at B. In other words, take the orientation for X at A, add to it the orientation for Y, and compare that with the ambient orientation of M. And the fact that these are going to be canceling is a statement that epsilon A plus epsilon B is 0. They're opposite signs. Okay. Well, you might say, well, you chose all these orientations, maybe matters. But since the manifolds are connected, a change of orientation of any one of the three affects both epsilon A and epsilon B by multiplying by the same integer, -1. So this statement is independent of the choice of all the orientations. Of course, epsilon A and epsilon B independently depend on the orientations, but the fact that they're opposite is independent, clearly. Okay, so that's the first assumption, that these are algebraically canceling intersection points. Okay, so I'm not going to formulate the statement of the Whitney trick. I'm just going to start constructing what you do in the Whitney trick, and I will end up with, I think it's 3 assumptions. This is the first, that the signs of the critical points are canceling. Okay. The next is that there exist arcs, arcs gamma x in x and gamma y in y through these points. So for example, if this is x, here's gamma x, and this is the point, let's say A is -1 and B is +1 on this arc gamma x inside x. And for a reason that will become clear in a minute, that's what I do. I think gamma of x being the coming from the x-axis. I'm going to think of gamma of y is coming from the unit upper hemisphere. So let's call it C. This is in the plane. So this is the upper unit hemisphere in the plane. And this will be B, and this will be A, and this will be gamma of y. Okay. So in other words, I have a map of this interval in the x-axis isomorphically onto gamma x. This part of the unit circle, slightly bigger than the upper hemisphere, going isomorphically onto gamma y. So together, these define a map of, let's call this part of the unit of the x-axis A, and let's call this part of the unit circle C. I have a map of A union C, which sits in R2. A map of A union C into the manifold, the ambient manifold. A goes to gamma x, C goes to gamma y. Okay. So here's what I have. So this is a picture in the plane, and it's embedded in M, these properties. Now I'm going to extend it to a neighborhood in the plane of this configuration. So something like this. Well, go ahead and extend these circles and intervals. Yes, I guess it's not quite a neighborhood. It's a neighborhood relative to the endpoints. And then, of course, to have a regular neighborhood, I have to take a circle out of the middle. So this is P naught, is this thing. It's just the regular neighborhood, in some sense, mod boundary of A union C in R2. Okay. And P will simply be P naught union this disk D. So P is diffeomorphic to a ball. It's contractible. Okay. All right. So now I'm going to extend the map from A union C into M to an embedding, of P naught into M, with the property that P naught intersect X is simply gamma X, P naught intersect Y is gamma Y. Gamma X is the intersection of P, with the X-axis. Gamma Y is the intersection of P naught with the unit circle. Okay. And otherwise, P naught is disjoint from M. And I want the normal vector. So for any point X in gamma X, the normal at X to gamma X is independent, is disjoint from the tangent bundle to x at this point. In other words, if x is a sheet and here's gamma x, then p is p naught, the embedding of p naught is actually sticking out, linearly independent from x. Okay, so this is gamma x, and this is a little piece of p naught, and this is x. And similarly for y. Or y in gamma y. P naught is sticking out from x and y. Sticks out from x along A, sticks out from y along C. Okay, well, it's easy to do that. I won't argue for that. That's fairly straightforward. So this gives me an embedding of P. Now I'm going to construct a bundle of rank R minus 1 over A union C. It's going to be called, let's say, CX over A union C. Okay. And its definition, it has completely different definitions over gamma X, over A, and over gamma Y. So if you restrict to A, you simply take the orthogonal, so I'm going to impose a metric here and just talk about orthogonal complements. You take the orthogonal complement of the tangent bundle of gamma X inside the tangent bundle of X. Okay, so we have X, gamma X. This bundle is simply the normal bundle of gamma X in X. Okay, so it's the tangent bundle of X is the dimension R, so this is a rank R bundle. Gamma X is a one-dimensional subbundle. I'm taking the complement, so this bundle over A has rank R minus 1. That's what I do over A. Over C, I take the perpendicular to the tangent bundle of P naught plus the tangent bundle of Y. So let's think about ranks here. So the rank of the tangent bundle of Y, so this is at some, well, let's work at a point. The rank at the tangent bundle of Y is S, which is the ambient dimension minus R. The rank of the tangent bundle of P naught is 2. P naught's a subset of the plane. But Y intersect P naught is C, which is a curve. So the rank of their intersection is 1, and hence the rank of the tangent bundle to P naught plus the tangent bundle to Y is K minus R plus 1. And therefore it's perpendicular is K minus this number, so it's also R plus 1. So let me just draw a picture of this. So we have Y, this is Y now, and here is gamma of Y and P naught sticking out. So the sum of these two bundles is of rank 1 larger than the rank of Y, which is S plus 1, K minus R plus 1, and therefore its perpendicular complement is of rank r plus 1. If we've arranged our metric, which is easy to do, so that at x and y, at a and b, x and y are orthogonal, the tangents to x and y are orthogonal, then you will see easily that these two definitions, the normal to y and p naught, things normal to y and p naught at either a and b, agree with things tangent to x and normal to gamma x. So these two fit together, these two definitions, these subbundles, they're both of rank k minus 1. These subbundles of the normal bundle of P naught in M agree at the 2 points of intersection at A and B. So together they form a rank rank R minus 1 subbundle of the normal bundle, which is of rank k minus 2. Let me see if I can draw a picture that's convincing. Yeah, so let's suppose that y is 2. Let me draw a picture where y is 2-dimensional and x is 1-dimensional. So this is x, this is y. X is, and this is also gamma of x, and here is gamma of y. Well, sorry, I should do it the other way. I should call this x and this y to fit with what I was doing earlier. So this is y, this is x, this is gamma of x. All right, so I'm interested in and then P naught looks something like this. Okay. The first part of the bundle is the normal bundle in x to gamma of x. So in this picture, it's a vertical bundle. It's the vertical. So that's what it looks like over gamma x. And what is it over gamma y? Well, it's supposed to be the perpendicular to y and p naught, jointly perpendicular to y and p naught. Well, in this case, y is contained in p naught, so it's just the perpendicular to p naught. So again, it's the vertical bundle, and this would be a section of it. So these, if you've made x and y perpendicular at these 2 points, these definitions will line up over A and B and give you a subbundle of the normal bundle of P in M over all of gamma x union gamma y. So I've got this rank rank R minus 1 subbundle of the normal bundle of P naught in M, which is a rank k minus 2 bundle, because M has dimension k and P has dimension 2, restricted to gamma x union gamma y, or A union C, depending on which set of coordinates you want to use. Okay. Next, we have to see homotopy theoretically, this is a bundle over a circle. Just remember what these two look like. So homotopy theoretically, it's just a circle, and I claim this bundle is isomorphic to the trivial bundle. Well, its isomorphism class is determined by whether or not it's orientable. We're working over a circle, basically. Well, that's a question of whether or not you have since x is oriented, gamma x is oriented, the normal bundle along gamma x is oriented, and likewise the normal bundle to p naught along y, gamma y is oriented. And the only question is whether or not the orientations, if you choose the orientation so they match here, do they match or are they opposite over here? Well, it's easy to unravel what that question means. And it turns out that these orientations match if and only if the signs of the intersection here are opposite. Because the signs of the intersection in the plane are opposite. So if you match those, then the normal directions will also be oriented. And proof, since epsilon A plus epsilon B equals 0, that implies that this bundle over the circle is orientable, but every orientable bundle over the circle is trivial, isomorphic to a trivial bundle. Okay. Okay. So I haven't made any more assumptions. I've just used my assumption that epsilon A plus epsilon B is 0. Okay. Next, let's consider the normal bundle, not of P naught, but of all of P inside A. Sorry. Next, I come to the second assumption. In P naught, we have a boundary component of P naught that is the boundary of the disk. I'm going to call that component boundary component alpha. And then I have the outside, which I'm not going to name. So the next assumption is that alpha bounds a disk, a map of a disk, D2 mapping into M minus X union Y. So that there is a disk. Well, yeah, you see a disk in the plane, you can map that disk into the manifold, extending the map you already have on alpha, and its image is disjoint from X and Y. So that's some sort of the homotopy class of alpha in this complement of X and Y is trivial. Okay, so that's one. And the other assumption is that the dimension of the manifold is at least 5. Okay. Well, then by general position, we can find an embedding of the 2 disk into M minus X union Y. That matches with the embedding of P naught into M near alpha. So using this embedding together with the embedding we already have of P naught, we get an embedding now of P into M. And P, okay. So what's a neighborhood of P look like? A neighborhood of P looks like P cross a ball of dimension K minus 2 of radius some epsilon. I won't say what the epsilon is, all right? Simply because P is now contractible, therefore its normal bundle is trivial. Choose a trivialization of the normal bundle, that will produce a diffeomorphism of a neighborhood of P and M, P cross a ball, where the original embedding is P cross 0, okay? We also have this bundle CX over A union C, and I can choose an isomorphism, a trivialization of it, A union C cross, well, let me do all of Euclidean space, not just the ball. So let's think about the normal bundles. So it's a trivial vector bundle, and this will be a trivial vector bundle of dimension r minus 1. So I have this trivialization, there's no choice in this trivialization up to homotopy because P is contractible. Any two will be the same. I have some choice here. No, I don't. The orientation is the only choice here. Okay. My next claim is that this bundle, C, extends over all of P to a subbundle of the normal bundle of P and N. So what kind of question is that? I have a trivial bundle of rank K minus 2 and a trivial bundle of rank R minus 1 over a circle. The first bundle's over a disk, the second bundle's over a circle. And I want to know whether or not I can extend this bundle over the circle to a subbundle here. Well, we can now, using these trivializations, we can identify CX with a map of A union C into the Grassmannian of R minus 1 planes in K minus 2 space. So at each point of A and C, I have a copy of R minus 1. It's embedded into RK minus 2, so it gives me a linear subspace in RK minus 2 of this dimension. And these are all oriented, Grassmannian of oriented planes. Okay. So the subbundle is really, with respect to the trivializations, I've chosen a function from this circle, slightly bigger version of the circle, into this Grassmannian of planes. But we know the homotopy type of this Grassmannian. It's Grassmannian of oriented planes is simply the orthogonal group of the ambient space, because any plane can be pushed by the ambient orthogonal group to the standard plane. And then we have to worry about what subgroup of the orthogonal group fixes the standard plane, dimension K minus 1. That's SO R minus 1 cross SO of the complementary dimension K minus R minus 1. Okay. When we have to calculate the fundamental group of this space, but K is at least 5, that implies the fundamental group of SO K minus 2 is Z mod 2. Right. And since these numbers add up to K minus 2, at least 3, one of the two of these is bigger than 1. So either R minus 1 is greater than 1, or K minus R minus 1 is greater than 1. These two numbers add up to something that's at least 3, so one of them has to be bigger than 1. That implies that the fundamental group of this product is non-trivial, and it maps onto the fundamental group of SO2. So pi 1 of SO R minus 1 cross SO K minus R minus 1, mapping to pi 1 of SO K minus 2 is surjective, and that implies that the fundamental group of this Grassmannian is trivial. And hence, this map phi is homotopic to the constant map. And that's all you need to be able to extend over this disk. Hence, C extends to a subbundle C tilde X K minus 1 inside the normal bundle of P in M2, in M. Okay. So I've now made 3 assumptions. The first assumption was that the intersection numbers at A and B were opposite. The second was that the ambient dimension of the manifold is at least 5. And the third was that this loop alpha we found by this inner boundary to P naught bounds a disk in the complement of X and Y. Those are my 3 assumptions. And at this point, I'm set up to do, I have everything I need to do the deformation. So now, using this, we write the normal bundle of P in M as P cross this bundle, cross B, a disk of radius epsilon, rank R minus 1. Sorry, this should be R minus 1, not K minus 1. It's the dimension of X minus 1. Cross complementary disk ball of radius K minus R minus 1. Okay. So P is dimension 2. This is a fiber dimension R minus 1. This is fiber dimension K minus R minus 1. So the total fiber dimension here is K minus 2, which is a complementary dimension of P in M. Okay. Now I do this in such a way that P cross B epsilon R minus 1 is the image of this extended bundle. Okay. All right. So in particular, what we have, so this is now a normal neighborhood, not a normal bundle. So the intersection of X with nu, let's call it nu, is gamma X cross B epsilon R minus 1 cross 0. Y intersect this neighborhood is gamma Y cross 0 cross B epsilon K minus 1. And you notice the dimensions work out. X intersect nu has dimension R, and Y intersect nu has dimension K. So now let me draw a little picture of what we have. Yeah, so now I'm going to use the same dimensions I did before, but reverse the roles of X and Y. So this time, this is going to be X. This is going to be Y. And we have this P, which is here. So, or the inside of P is there. Okay. And I have this normal bundle, which in this case is, well, a normal thickening, which in this case is vertical. And what I'm going to do is push a neighborhood of gamma X across this disk to the other side of Y, and do it in such a way that near the boundary is no change in X. So let me think how I'm going to do that. the coordinates I want to set up here. Okay, so the first thing I need is an isotopy of gamma x, or A, switching back and forth between the two notations, inside P. So here's P, here's gamma x. I want an isotopy of the form, let's call it J of U and T. So U is a parameter for gamma x. It's the coordinate along gamma x. T is the isotopy parameter. And I'll draw a picture of what the isotopy looks like. First of all, it's the trivial isotopy near the boundary of gamma. And it starts pushing as T goes along. It pushes this, I don't have much room there, until you push the axis, keeping its neighborhood of the endpoints fixed, so that it lies up above the unit disk, as this picture is supposed to indicate. So so J of U will be of the form U comma psi of U and T. So in other words, these are all going to be graphs of functions of gamma x into the y direction. Okay, with the following properties for psi. Psi of U T equals 0 for all T U near boundary gamma x. Okay, so psi is identically trivial 0 out here near the boundary for all T. Of course, psi of U 0 is also 0. This isotopy is going to start at the given embedding, x naught along the gamma x along the x-axis. And the last condition is psi of U T for psi of U1 is outside the unit disk, the intersection of the unit disk with P. So this is an isotopy, gamma x cross I into P. And notice, of course, it's crucial that I've filled in this disk, otherwise there'd be no way to do such an isotopy. But filling in the disk allows me to do an isotopy. All right? That's one piece of the ingredient to do the deformation of x. The other piece is a function from this ball of radius epsilon, of dimension k minus 1 to 0, 1. And here's its graph. It's going to be 1 at the origin, and it's going to be 0 near the boundary. And if you want, it can just depend on the radius coordinate, but it doesn't really matter. Okay, so omega of the origin is 1. Omega is identically 0 near the boundary. And of course, it's a smooth function. Okay. All right. So those are my two ingredients. And now here is the isotopy. I'm going to have an isotopy of gamma x cross the ball of radius epsilon, the first factor, cross 0 in the second factor. Remember that this is x intersect P. Okay, it's going to be an isotopy from there into where's it go? Into P cross B R minus 1 epsilon cross 0. So the 0 is just going to come along for a ride. So it's an isotopy. So this cross I mapping into here. Okay, so our coordinates here, we have a u, that's the coordinate along gamma x. We have a vector x in r-1 space of norm at most epsilon. We have 0, that's just a placeholder. And we have the isotopy parameter t. And we're going to send this to, well, u omega of x times psi u t x 0. So we're going to do this, the isotopy that psi described, but modulated by this function omega. So at the origin, what happens at the origin, omega is 1, and so let's call this k. K of u 0, 0, 1 sits inside P, and it is this loop. Because this is always a graph of a function. In this case, t equals 1, so psi ut is this function that's above the unit disk, and omega is 1. So we haven't damped out this isotopy at all when x is equal to 0. So that's the image of gamma x. So under this isotopy, gamma x moves across the disk to be on the other side of y. Yeah, so in this picture, remember, this is y and this is x, pieces of x and y. Okay. So we have to check several things. We have to check that k is the trivial isotopy near the boundary. So k u x 0 t equals u x 0 for all t for u close to the boundary. Sorry, gamma x. And that's because for u close to the boundary, psi is 0. Doesn't matter what x is. This coordinate's always going to be 0. So u x 0 t for u near the boundary goes to u 0, which is just u. Yeah, x 0. All right, so so I have to explain this slightly differently. So k, remember, k is an isotopy from gamma x across the ball, across the isotopy parameter, into p across the ball. So as we saw here, gamma x 0, 0 at level 1 goes into p to give this curve. So now I'm interested in what the isotopy does when u is near the boundary. So this is u comma 0, u comma 0 comma x comma 0. Let me write that a little bigger. Okay. So u is a point in gamma x. Its first coordinate is supposed to be a point in p. It's just u again, but I have to write it as u0 because it's now a point in the plane. So it needs two coordinates. U is the x coordinate. 0 tells me I'm just on the x-axis. X is unchanged, and 0 comes along for the ride. And the reason is that whenever u is sufficiently close to the boundary of x, psi is 0, so it doesn't matter what omega x is. This coordinate's always 0. So you end up in U0, X, 0. Okay. So near that part of the boundary, this isotopy is constant. That's when U is going to the extremes. What about when X is going toward epsilon? So K of U, X, 0, T equals U0, X, 0 for all X close to boundary of the ball, R minus 1. The reason for that is near the boundary of the ball, omega is 0, and therefore it doesn't matter what psi is, this product is 0. So you end up with U0x, U0x. So that shows that near the boundary, this isotopy is trivial. The last thing I need is that K of gamma X cross B R minus 1 cross 0 cross 1. So the end of the isotopy is disjoint from Y. Well, remember Y is given by gamma Y cross 0, well, nu intersect Y. It's gamma Y cross 0 cross B K minus R minus 1 epsilon. So it sits in the other factor. So how can the result of the isotopy meet a point like this? I claim it can't. So the first thing you see is that X is 0. If you're going to have a point of intersection, that will imply the X coordinate, which was in the first factor, is 0. But anytime X is 0, omega of X is 1, T is 1, so this is the blue curve down here. U 0, 0. So when X is 0, the image of this isotopy at time 1 intersected with where X is 0 is simply the curve here. Simply this curve here, which is disjoint from the intersection with Y. So X equals 0, that implies that, well, the image of K at time 1 of gamma B epsilon R minus 1 intersect X equals 0 is U psi of U1, which is disjoint from Y. Okay. So let me try to draw a picture. Well, in the case that I had just a minute ago, when Y is 2-dimensional and X was 1-dimensional, looks like that. Here's the disk, and the effect of this isotopy, gamma X is equal to X, so there's no normal disk in the X direction. You're just pushing this loop across this 2-disk until it ends up behind the 2-disk back here. So that's the isotopy. You just push across and you remove these 2 points of intersection. Okay. Maybe a more interesting picture is to take the case when X is a surface. See if I can draw that picture. And Y is 1-dimensional. Okay, here's gamma of X. This time we have this normal bundle. There is a non-trivial normal bundle. I've extended it over the entire disk. Okay. And now what I'm going to do is push, for gamma x, I'm just going to push gamma x until, well, I start out here slightly. I mean, I have to, gamma x is extended past its intersection with y. And so I'm going to push gamma x just like I've described before. It's going to go out. I'll do it in blue. Gamma x is going to go out and around out here and come back. That agrees with what's happening, what was originally happening out there. It's a trivial isotopy toward the end of the gamut. But now that's what happens at level 0, but somehow I have to move back at level, so that by epsilon, I'm back where I started. So I have a trivial isotopy. So what's going to happen is there's going to be a cup. This thing is going to come over the top and come back here like that and go underneath the sheet and come back here. So you make a little cup-like region like that, which is bowed out even more. Let me try to draw the picture better. Okay, so I'm going to have a cup. Yeah. I'm going to have a cup like this. These are the front edges. And here's what the side will look like. There's another, and then the back will bow out. And there's another side here. Okay. Okay, so that's what you've done. You see the isotopy agrees out near the boundary with what you started with to begin with. And therefore, I guess the next step is, since K is a trivial isotopy near the boundary of gamma x cross b epsilon r minus 1, it extends to an isotopy of x trivial outside this region. Okay, so we have an isotopy of all of x, which is concentrated in this neighborhood, gamma x cross the ball, trivial on the boundary, so you extend by trivial outside, and you have removed 2 points of intersection without adding any other points. Okay, so that is the Whitney trick. Just to repeat what we needed complementary dimension submanifolds, 2 points of orientable, 2 points of intersection of opposite sign, arcs on each of the manifolds connecting those points, and dimension at least 5, and this homotopy condition that the loop, which is basically the loop gamma x, gamma y, pushed in a little bit, bounds a disk in the complement of x and y. Then you can deform x by an isotopy to remove those 2 points of intersection, creating no new points of intersection by an isotopy concentrated in a small neighborhood on x of the arc connecting the 2 points. Questions about that? So that is the Whitney trick. All right. Let me go on and show you how this applies in the context of, oh, I guess I won't go on and show you how it applies since I've run out of time. All right, I'll show you the application to reduce the second cancellation theorem to the first. It's a fairly simple argument now that we've done this. I just have to check these hypotheses, which are not too hard to check. I'll do that next time. If there are no more questions, see you,
Thank you.
next week. Going, gone.
So,
Oh, was there a question? No, somebody
do
saying
you
goodbye?
think did Snail have paper with him on the beach in Brazil, or do you think he did this all in his head?
Well, the Whitney trick was due to Whitney. It's much older. Yeah, I think the story is that he discovered the proof on the beach. So I'm not sure which was the last step for him, which was clear. He already knew and where he had to do some work. I don't actually know. And I think he wasn't thinking, my understanding is he wasn't thinking so much in terms of Morse theory as in terms of Handel theory. Now, they're very closely related, but as I sort of indicated when I drew the two different pictures for the Handel slides, even though they're mathematically equivalent, they present very different pictures or give you very different insights into what's going on. And I think he was working much more in the Handel theory. Maybe it was the Handel slide, I'm not sure. But yeah, it was on the beach, if we're to believe the stories. All right, see you next week.